It's not easy. I'm going to be.
Okay, covering your homework if you haven't already. Okay, so a couple of people asked if I could go over one of the Diels-Alder reactions. And I'm not going to do one that was on the homework because I've hopefully already done those, but I'll do one that I think looks kind of similar and maybe the same amount of scary. I don't know. So I feel like this is sort of in the realm of the stuff that was on the homework, right? So one of the challenges I think that people are facing is how to sort of redraw or reorient the molecules so that the sort of the process and the mechanism that you know of drawing the arrows and making the bond to make the six-membered ring is a little bit easier and more straightforward. So both of these reagents here, we're probably going to want to redraw in a way that makes them look nicer and more Diels-Alder-y, I guess. So let's start with the diene. Well, first of all, we want to identify what's the diene and what's the dienophile. So we've got two conjugated pi bonds there. And here we've got, well, we also have conjugated pi bonds, but we only have one alkene. Here we have two alkenes. So this is going to be our diene, and that's going to be our dienophile. Drawn them in the same order that I usually do, and I will on the exam. But, okay, so we usually like to see the diene drawn like that, right? So let's see if we can rotate some of the bonds here and see if we can kind of make this shape. So let's have our the top double bond here be this one. So what we can do is we can take this CH2 group at the end and the methoxy group and sort of flip them. That's okay because we can rotate, we have free rotation around this single bond. So that means that the methoxy group can go there, and just drawing this line for the methyl group is the same as writing the CH3. And then on the other alkene, we've got an ethyl group on this carbon. So there's our diene. Okay, what about the dienophile? So there's the alkene that's going to react. It's the only alkene in that molecule. And so really everything else that's on it is kind of superfluous. And so we can take this ester, it's an ethyl ester, that's the same on both sides, and we can rewrite that as CO2ET, just to abbreviate it, or if you really want, you could just write R. It doesn't matter. And so that means that we've just got a double bond. And then in trans configuration, right, because those are on opposite sides, we've got an ester trans to an ester. Or you could write R or sort of whatever placeholder that you want. In this case, we just have to make sure that the alkene is trans. Okay, so at this point, we can do the mechanism. So I'll draw the bonds that are forming here. There we go. there's our arrows. And now we're forming a 6-membered ring. Like that. That's where our double bond's going to be. And now we just have to fill in all of the decorations that are sort of on the that were on the starting materials. So the methoxy group is still here. The ethyl group is there. These carbons don't have anything on them, and those are those middle carbons. And then for this part over here that used to be the dienophile, we've got trans configuration of the ester groups. And so that means one of them needs to go on a wedge. And one of them on dash bond. And so we could also write that out fully if we wanted. There's ester. So, does that make anyone feel a little bit better about rearranging the molecule a little bit? Not really. So, the main thing I would say to keep in mind is that you're looking for this the diene and the dienophile somewhere in your starting materials. You can always join those carbons together in that fashion and get a cyclohexene. Okay. Okay. Questions on this? Yes.
I'm just that you uploaded like a lecture that you recorded from last week, right?
Yes, I'm going to keep recording them. They'll all be on the Panopto thing. Yeah. Yes.
Can you show us how you like restructured the second edition?
How which structure?
The second edition.
You're talking about the difference between these two?
No. If you go up with the original problem,
Yeah.
you have the base of the dying profile, and you're adding the ester.
Yeah.
But how do you restructure it? Because like, then when you go down, you have you just simplify it to that.
Yes. How did I do that?
Yeah.
Okay. So what I've done is for the dienophile, the part that's going to react with the diene, which is here, is this CC double bond. And so what I did is I said, okay, I don't really care about the rest of the molecule, this double bonded oxygen and this oxygen, all that stuff. Those are going to be that. It's going to be there in the starting material, and it's also going to be there in the product. But it, can, I don't want to say it'll get in the way, but in your head it might sort of get in the way of doing the mechanism and drawing out the reaction. So one way we can simplify that is to sort of abbreviate it in like element symbols. So the CO2 ET comes from that carbon, that's the C. O2, it's got 2 oxygens, and then ET is the ethyl group that's here on the end. So if the other way you could write it is just like that. And then the product at the end becomes R and R, and then now that right, so when you have this simplified molecule, that makes it a little bit easier to draw the arrows. And then at the end, once you figure the product out, then you can say, okay, now I got to replace R with all of this stuff up here that we don't really care about. And that's how we get to the final product. Okay, I'll post the answer key for the problem set this afternoon, and make sure you take a look at that, and hopefully that will help clear some stuff up as well. Okay, so let's start talking about aromatic compounds. So we've certainly seen some aromatic compounds already, but didn't really talk about why they were the way they were. So kind of the old definition of aromatic is just any derivative of benzene. Now, the reason I specify that that's a historical definition is because we're going to find that there are aromatic compounds that aren't derivatives of benzene, but it gives you a general idea, at least for some simple aromatic compounds. So as a reminder, benzene is this guy, C6H6. And another way that we can draw benzene, can draw it out like all the way entirely. Double bonds there. So we usually show benzene as having alternating single and double bonds, because frankly that's an easy way to draw it. But we can draw at least one resonance structure of benzene, and all we do in that case is take each double bond, or each pi bond, and move it around the ring. So it kind of looks like a pericyclic reaction. And I guess it kind of is, but once we do that, we're going to get that, there, and there. So looks the same because it really is the same. But that just goes to show that if you've got some aromatic compound with something on it, it doesn't matter if you draw the double bonds like that with the vertical one on that side or the vertical one on the other side. Right? Same resonance structure, same compound. One thing that is common with all resonance structures of the same compound is that the real structure is just an average of the resonance structures. So from that we get something that looks like maybe this. And in this particular case, kind of the ring of dots here shows that we don't always have a double bond between each carbon. So here, that's a single bond. It's a double bond here. And so, kind of what this structure is showing is the bond order, or the level of single, double, triple bondness of each of the carbon-carbon bonds in benzene is 1.5. So rather than thinking of them as each being alternating single and double bonds, the reality of the situation is that they are all single and a half bonds. That does a better job explaining the stability and the reactivity of benzene. So, it's not unusual to see benzene like that. The hexagon with the circle in the middle. This isn't, it's not wrong. It's correct. But you should be wary of this circle. It's called a Clar sextet, and it means 6 electrons, or really 6 pi electrons. So for benzene, that is an accurate description. We've got 1, 2, 3 pi bonds in benzene, and each pi bond is made of 2 electrons, so we've got 6 pi electrons. The problem with this is but you can't use it to draw mechanisms, because in order to draw mechanisms, you really need to have those pi bonds drawn out fully. And when you've got more than one aromatic ring attached to your structure, you have to be careful. So this is naphthalene. It's got 10 pi electrons because it's got 1, 2, 3, 4, 5 pi bonds. And you might be tempted, based on this circle, and I know I certainly did this a lot when I was an undergrad, and now I kind of laugh at myself for it. You might be tempted to draw that. But this has 2 Clar sextets, so that's 2 times 6 electrons. And you can't fit 12 pi electrons into that aromatic system. And so drawing adjacent aromatic rings with circles in them is illegal. Yes?
If you were to take that and like make the one on the left a circle and the other one 2 lines, would that be it?
You read my mind. That is the next thing I was going to talk about. And that is correct. You can have that. That's okay because you've got 10 pi electrons, 6 plus 4. Questions on that? Cool. Okay, so we'll do a little bit of nomenclature. There's a few cases where this is actually a little bit important as we get a little further along. But unsurprisingly, for naming aromatic compounds, we're going to treat benzene as the parent in most cases. So that aromatic ring with an ethyl group going to be ethylbenzene. If we have a chlorine atom, then that's going to be chlorobenzene, and so on and so forth. For monosubstituted benzene rings, that's fairly straightforward. You just use benzene as the parent. There's also some common names. For a few of these. methylbenzene is toluene. Methoxybenzene is anisole. Aminobenzene is aniline. Benzene with a carboxylic acid is benzoic acid. If instead of a carboxylic acid, it's an aldehyde, then we have benz aldehyde. And then we've got two more. Benzene with an alcohol group is phenol. And with an acetyl group is acetophenone. So those are a few that you might see, especially toluene and benzoic acid. Those are pretty important ones. So if we have a small substituent, then we can call it methylbenzene or methoxybenzene or something like that. But if the substituent is more than 6 carbon atoms, then we usually have that other bigger group be the parent group, and then the benzene ring becomes a substituent. So if it's just a benzene ring, that's a phenyl group, and we use the symbol pH, and that always represents C6H5. So yes, 1, 2, 3, 4, 5, 6, 7. So we could call this heptyl benzene by that method where benzene is the parent. Or we could say that 1, 2, 3, 4, 5, 6, heptane is the parent, and it's got a phenyl group on it, a C6H5. And in fact, if you count, there's 1, 2, 3, 4, 5, 6 carbons, and 1, 2, 3, 4, 5 hydrogens. So that is a phenyl group. So that's phenylheptane, or 1-phenylheptane if you like. Or we could draw this pH, 1, 2, 3, 4, 5, 6, 7. So we can just replace that monosubstituted benzene ring with a pH. Now, if we've got other things on the benzene ring, let's say we've got some multiple things, and I don't know, maybe we're interested in the reactivity of that carboxylic acid, and we don't really care about the aromatic ring, we can refer to this part as not a phenyl group, but an aryl group. Because it's not phenyl, it's not C6H5, but it's still aromatic. And we'll call that an aryl group, or AR. And we're going to use that just like we use the letter R for just some organic group. And so you could write this as AR for the aryl. And that way, if we're just concerned with doing something with the carboxylic acid, we don't have to draw out the whole aromatic group. The aryl group can also just be a phenyl group. So it can be a catch-all sort of for anything aromatic. Yes?
So it's an aryl group because of the attached carbons in the benzene?
Right. We couldn't write pH because that would imply that those methyl groups are not there. Okay, so in these cases, well, except for the aryl group, the benzene ring has only had one substituent, but say we've got multiple substituents on the benzene ring. For example, we're going to look at dimethylbenzene, which is also called xylene. And if I asked you to draw the structure of dimethylbenzene, there's 3 different isomers. So there's one where the 2 methyl groups are right next to each other. There's one where they're in that position. And the last one where they're on opposite sides of the ring. So these are all dimethylbenzene, but they're different isomers, and so we need to be able to tell them apart. The most straightforward way, and the way that you probably know how to do this, is with numbering. And you can do it that way. So you can say, all right, if we're going to call this top carbon, carbon 1 in each case. And so these are 1, 2. So this is going to be 1, 2 dimethylbenzene. This is 1, 2, 3. And this is 1, 4. Okay, that's...
Because dimethylbenzene is just the model version of xylene, you could just write xylene or dimethylbenzene, is correct?
Yes, we're going to make it even easier than that, though.
Okay.
Yeah, so this is to, even if you use xylene, this would be a little bit tedious. So as it turns out, there's a better way to describe the position of the substituents on the ring. And this particular nomenclature can only be used for benzene derivatives. So if you've got a cyclohexane ring, which is just benzene without the double bonds, you can still use this 1,2, 1,3, 1,4 notation. But this new nomenclature is exclusive to benzene rings. So this 1,2 relationship is called ortho. 1,3 is meta. And 1,4 is para. And so we abbreviate those just with the first letter. And so this compound is orthoxylene, or just O-xylene, meta-xylene, and para-xylene. So the mnemonic device that I use for remembering these, it also has to do with a methyl group being one of the substituents, but it doesn't just have to be a methyl group. They could be hydroxy groups or alcohols, and then we would have ortho dihydroxy benzene or whatever. But anyway, so this position is ortho. This position is meta. And that position is para. And so you just have to remember chomp. So let's do a little practice. So for this molecule, we have the parent for this is going to be toluene because we've got a toluene molecule there. And then we've got a chlorine right adjacent to the methyl group. So that relationship is ortho. And so this is going to be ortho chlorotoluene. If we look for a parent here, methoxybenzene, without that nitro group, is anisole. And we have a nitro group, and it's at that position, so that's meta. And so this is going to be meta nitroanisole. We could also have something like that, where we have an NH2 group and a CH3 group on opposite sides. In this case, we can come up with two different names that are both correct. One of them has the parent being that, which is aniline. The other as the opposite where we consider the parent group to be toluene. If we consider aniline to be the parent group, then we have a methyl group, and it's at the para position on opposite sides, para position. And so that would be para methyl aniline. And then if we look at it from the perspective of toluene, we have an NH2, that's an amino group, and it's at the para position with respect to the methyl group. So it could also be para amino toluene. Now, the thing to notice about this is regardless of how you name it, it's para in both cases, because the relationship between the groups doesn't change based on which one you're considering the primary group and which one you're comparing it to.
Could they also be on opposite sides?
Yes. I think I know what you're asking. Yeah. Yeah, so these are both.
Like for the ortho and meta. Not necessarily para because it's.
Yeah, so this same thing would apply to this one. You could also call this ortho methyl chlorobenzene. In that case, you're considering chlorobenzene to be the parent, and you're saying that the methyl group is ortho to it. Yeah, so the relationship from one group to another, like from group A to group B, is always going to be the same as the relationship from group B to group A. Questions on ortho-meta-para? Yes? Yeah.
How are we reading the Like, where are we getting the amino?
The amino is from the NH2. That's an amino group. I'm not going to ask you to come up with these names on an exam, but you're going to need to know the ortho, meta, and para substitution patterns. Yes.
So the aniline comes from the CH3?
Aniline is benzene with an NH2
Okay.
on it.
What did you say about the amino that came from the NH2? Or did you just say it came from the CH3? Sorry, I was.
No, it's okay. So that's aniline. That's toluene with a CH3, methylbenzene. And so for para-aminotoluene, we're considering it to be a toluene molecule. And the para-amino part means that at the para position, there's an amino group, which is an NH2. So CH3 and NH2, that's the same molecule. For para-methyl-aniline, we're saying, okay, we have a derivative of aniline, which is this, and then at the para position, there's a methyl group. I don't know why I felt the need to come over and point at the actual board rather than point here, but yeah. Okay, so, and then if you've got more than two substituents, then you have to resort to using numbering. So this molecule, 1 methyl group and 3 nitro groups. So let's have this be a derivative of toluene. And if toluene is the parent molecule, that means that this carbon is number 1. And so this is going to be 1, 2, 3, 4, 5, 6. 2, 4, 6 tri nitro toluene, which is TNT.
It's just abbreviated that way, or that's totally written? It's abbreviated that way?
TNT, like the explosive?
Yeah.
Yeah, that's where the name TNT comes from. It's trinitrotoluene. Okay, so when we started talking about conjugated pi systems, we did a thing where we showed the hydrogenation of these conjugated dienes, and we said that the conjugation makes the dienes more stable. And we're going to see the same thing happen with benzene. And so its stability is really high. It's like unusually high. So remember, from addition reactions to alkenes, those are reactions that you can do. So you can take something like that, cyclohexene, you can treat it with elemental bromine at room temperature, and you add 2 bromine atoms across the double bond. But if you try to do this with benzene, it's not going to work. So if you take benzene and you treat it with bromine and you like cook it at 300 degrees, you're not going to get a reaction. That's 25. Yeah, so at room temperature that reaction will occur, but even if you do this, if you try and do the same thing with benzene, even if you heat it up, it's totally unreactive toward bromine, which as a halogen is a pretty harsh reagent. So those conditions would destroy that 300 degrees, that would destroy a lot of organic molecules. So we can compare some of the thermodynamic data from these reactions to actually see what's going on here. So if we take cyclohexene and add hydrogen, so hydrogenate it, with a catalyst and at 2 atmospheres, so slightly elevated pressure, we're going to get cyclohexane. And the enthalpy change for this reaction is minus 120 kilojoules per mole. So you can hydrogenate benzene. You have to use a slightly different catalyst, but you have to increase the pressure to 150 atmospheres, which is kind of nuts, but you can do it. Now, if you look at the enthalpy change for hydrogenating cyclohexene, it's 120. So we've basically just got 3 cyclohexenes, just all in one molecule. And so that would kind of imply that we should be looking for a delta H somewhere in the range of minus 360, which is just 120 times 3 for those 3 pi bonds. We should be looking for minus 360 kilojoules per mole. But if you actually do this experiment and measure the enthalpy change, you'll find that it's minus 208. So that's a pretty big difference of like 150 kilojoules per mole. So, okay, what does that tell us? If we expected benzene to be 350 kilojoules per mole higher in energy than cyclohexane, in the same way that we said, okay, we've measured this reaction and we found that the energy difference between these 2 molecules is 120. We assume that the difference here should be 360, but it's not. It's smaller than 360. And so that tells us that benzene is lower in energy and lower in energy means more stable than we would expect it to be. So, one of the reasons for this is, well, first of all, it's a conjugated pi system. And in that regard, this analysis kind of thing is the same thing we did in the last chapter when we looked at the conjugated dienes. But there's one more thing that's involved. And it's kind of similar, so it's not like groundbreaking or anything. All right. So here's our frankly kind of ugly benzene ring. And if we look at the molecular orbitals, they're all going up and down from the plane of the ring. So Benzene is planar or flat. And it's a conjugated pi system. And so what that means is when we've got something like this, all of these shaded orbitals can interact with each other and share their electrons, or the lobes can. And then all the white ones can as well. And so we get sort of a smearing of electrons around the ring. And you end up with this like molecular orbital hamburger kind of thing, where both of the buns are these areas of electrons that can go all around the ring, and they can just spread themselves out. And so that gives us extra stability because we've got more places for those electrons to go.
No hamburger or no hamburger?
Molecular orbital.
Molecular orbital. Thank you.
Really small hamburger, so I guess there's not much hamburger. No hamburger. Okay, so we've talked about benzene being the prototypical aromatic compound, and it is. But there's plenty of other possibilities. And so there's 4 important criteria that we use to determine if some compound that we run across is aromatic. So the first is it's got to be a ring or groups of rings that are attached to each other. The molecule has to be planar, at least the part that we're claiming is aromatic. It's got to be flat because of this molecular orbital thing. Third, we've got to have that conjugated pi system. Again, same reason. And then there's a fourth and interesting criterion. It has to obey Huckel's rule. Okay, so what's Huckel's rule? Huckel's rule states that for something to be aromatic, we have to have 4n plus 2 pi electrons, where n is any number, any whole number. So let's just look at Huckel's rule, not the rest of the criteria. But for that molecule, cyclobutadiene, we have 1, 2, 3, 4 pi electrons because we've got 2 pi bonds. And 4 is not 4n plus 2. You can't make 0 as n doesn't work and 1 as n doesn't work. So this fails Huckel's rule. Benzene, okay, well we know benzene's aromatic, so it sure as heck better pass this rule. Benzene has 6 pi electrons. And that is 4n plus 2, because if n is 1, 4 plus 2 is 6. And so that passes the test. That is cyclooctatetraene. So we're just expanding the ring a little bit and adding another pi bond. 1, 2, 3, 4 pi bonds, so that's 8 pi electrons. And what about that? Does that pass or fail the test? Yep, 4n plus 2, you can't make 8 out of that, so that's a fail. Okay, so in summary, for a compound to be aromatic, it has to pass rules 1 through 4. All right, those are just the criteria for being aromatic. A compound is non-aromatic if it fails any of rules 1 through 3. Okay, so if it's not a ring, or it's not planar, or it doesn't have a conjugated pi system, it's non-aromatic. Notice that doesn't include rule 4, and it's because that sort of creates a separate category. Of anti-aromatic compounds. And anti-aromatic compounds are rings, are planar, do have conjugated pi systems, but then they fail Huckel's rule. Yes? No, it's okay.
Could you please draw the little numbers in the couples rule? Because I feel like when I come back later, I'm gonna wonder why it passed and why it failed.
Okay. So when you say draw the numbers,
When you're counting the carbons.
I think she just means insert it into N.
okay. So maybe you're talking about counting the number of pi electrons? Okay. So so for this, each pi bond is 2 pi electrons. So this is 2, that's 2. There's 2 there, 2 there, 2 there. And then 2, 2, 2, 2. Okay, cool.
Question.
Yes.
So when you're doing the formula, what is N exactly?
In N is a whole number, so 0, 1, 2, etc. So if N equals 0, then that's 2 pi electrons. There's really only one case where that occurs. If N equals 1, that's 6 pi electrons, so benzene passes. N equals 2, that's 8 plus 2, so 10 pi electrons. So if you have 10 pi electrons in naphthalene, 1, 2, 3, 4, 5 pi bonds, so 10 pi electrons. That passes the test as well. Okay, so okay, assuming that all the compounds are planar, because it's kind of easy to tell when things aren't planar, but sometimes hard to tell when things are planar. Assuming these are all planar, go through it and figure out if you think these are aromatic, non-aromatic, or anti-aromatic. You're good. Thanks. Sorry. Thank you.
Okay, the next one, this one. There isn't a zero versus so this one's already. There's a conjugated line system that drains. Assume that it's we assume it's planar. So then 2 4 6 8 so 14 leaves over here. So 14 that's 14. Yes, it passes. Yeah. That's not no, what is it? Our high ones are supposed to equal anything. So It doesn't matter if you actually get it back. Like, it's always gonna be just because like it's really
Are we gonna be reshaping these, or are they just say what they want?
Reshaping.
Like, the second one, you read like, can we fold it into them?
Yeah, but you can't make a bond that's not there.
that isn't. Because you're just floating
It's like someone is talking.
So if it passes something, that means 4 inches of safety.
You would have to
Right, so if G equals 0, that's 2 pounds.
We're most using our.
That's 6 pounds. So you can't have.
That is my most using. It's that in the one.
I do get what you're saying, and I think I'm I think so, because, forget last year. No, I forget, I'm not involved, I
Okay, what's the first one? Anti. So it's a ring, it's planar, it is conjugated, but it's got 4 pi electrons, which that does not pass Huckel's rules. Another thing, maybe I pointed this out, is for Huckel's rule for something to pass Huckel's rule, you have to have an odd number of double bonds. I guess it's easier than 4n plus 2, but so benzene with 6 pi electrons has 3 double bonds. 3 is an odd number, so it passes on this rule. The second one, the linear one, what is that? Non-aromatic. It's not a ring, so wah wah. The third one, that's also non-aromatic because it's not conjugated. And then the final one is anthracene. Yep, that one is aromatic.